The next speaker is Professor Kyed from Flensburg University of Applied Sciences. And the title of his talk is Fluid Structure Interaction Under Periodic Forcing. So please.
Thank you. Thank you for the introduction. So I will start with a brief summary of the main problem that I'm investigating. I'm mainly focused in the damping effect that a viscous fluid has when it is in contact with a deformable structure. And the deformable structure I'm looking at is an elastic plate, a deformable plate, whose motion is governed by the plate equation. So here you see the plate equations, and the red term d of u is a damping term. My damping term here in this setting is some very general nonlinear term. But of course, in a moment when I couple my elastic plate with a viscous fluid, the damping will be the force. The damping term will simply be the force coming from the fluid. But this is a nonlinear damping term in that case. Okay. I introduced in my last talk what it means for a damping term to be sufficient to prevent resonance, and I defined this notion as being, or this property as being true when for some maybe small epsilon, any time periodic force, no matter which frequency, leads to, or at least for every time periodic force of maybe small frequency, there is a corresponding time periodic solution. In this case, it's reasonable to say from a physical point of view that resonance or that the damping is good enough to prevent resonance. Okay, so so that will be my main focus, showing this, the existence of such time periodic solutions. Okay, how do we show existence of a time periodic solution for small data? Well, in the nonlinear case, if my damping term d is nonlinear, I linearize it and look at the linear operator. Look for some good spaces, and these spaces, the best spaces is where I have the maximal regularity. So I say here I'm looking for good time periodic maximal regularity spaces. If I have a good time periodic maximal regularity, I may be able to close a fixed point argument and thereby showing existence of a time periodic solution to my nonlinear problem, and that's what I want to do. Okay. So that's the general notion of when a damping term prevents resonance. Then I moved on to the specific case of an elastic plate being in contact with a viscous fluid. More specifically, I considered a container with a viscous fluid, and on top of this container we have an elastic plate which is in contact with the fluid. We exert on the elastic plate periodic force. This is my PER, periodic force, and so of course the plate will deform, and the motion of the plate will set the fluid into motion. In a viscous fluid, I have energy dissipation, so I have a damping effect, and my main goal is to quantify, in fact, this damping effect. And then, of course, once I have quantified it in a good way, in the sense of maximal regularity, in fact, once I have quantified it, identified good maximal regularity spaces, I hope I will be able to show that, I mean, that's the main result. In fact, that's where I want to go today, show that show existence of time periodic solution for any forcing sufficiently restricted in amplitude. Okay. When we couple the fluid with the plate, we have no slip boundary condition on the fluid surface, the fluid structure interface. And of course, we have the plate equation to govern the motion of the elastic plate. And the red term you see is the force coming. Here's the force coming from the fluid. So that's the force exerted on the plate by the viscous fluid. In the plate model, we consider only the normal component of this force. So capital N is the normal vector in the current configuration, so in the deformed configuration, and small n is the normal vector in the reference configuration. So in my case here, it's 0, 0, 1. Okay, so let's see. That's a coupled system fluid structure in my case. And of course, my nonlinear damping term in my plate equation is, well, exactly this force term from the fluid. And you can, of course, interpret or view this force term as a function of u, because in the fluid equation, the only input in the Navier-Stokes fluid equation is the deformation, is the displacement u of the elastic plate. So we have here, in fact, a function of u, because the velocity, field, and pressure of the fluid can be viewed as a function of u. So I have here a damping term, which I write as d of u. Okay, so I should say, if I did mention this already, that in the plate equation, the small u denotes the displacement of the plate in normal direction. And in the plate model, you assume that you only have displacement in normal direction. Okay, so then I went on to investigate a model in which I introduced also in the plate equation an internal damping mechanism. The term dt Laplace u, you see in blue, in the plate equation on this slide, is a very heavy damping term, in fact. So this may seem strange that I want to introduce an internal damping in the elastic plate when what I'm in fact want to investigate is the fluid damping, so the red damping term here. There is a reason for this, and I will try to explain you the reason why I start with this damping term. I want to end in my talk on Friday, that's tomorrow, by studying the case without this internal damping. But for now, I add this internal damping. Okay, so that's the model, the first model that I want to rigorously investigate. Okay, so I'm looking for, I want to show existence of time periodic solutions for arbitrary, but maybe in amplitude restricted time periodic forces. I do this just as in Professor Shibata's talk by setting my equations in a or expressing my equations in a framework where the time axis is the torus, which I denote by t. In that case, everything is time periodic by nature, so to speak. I also introduce periodic boundary conditions in space, and I do this by expressing my equations in the spatial domain, which is also a torus. That way, I have boundary conditions, periodic boundary conditions in two spatial directions. That's not, from a physical point of view, the most reasonable boundary conditions. I admit that, but it is from a mathematical point of view, for this problem, the simplest boundary condition. And so I start with this. And one of my goals, in fact, and I will speak about open problems and outlook at the end of my talk, is to be able to show some of these results here also in more complex geometries. Okay, and complex boundary conditions. Okay, so once I have introduced the torus as a time axis and also the torus, the space for the space, two spatial coordinates, x1 and x2, I end up with the system you see here, my equations of motion for the fluid plate system. So we have the Navier-Stokes equation, we have the no-slip boundary condition for the velocity field in the Navier-Stokes equation, and we have the plate equations describing the displacement u of the elastic plate. This is a kind of a volume condition that I also need, which is also natural as a volume condition, and everything is set here in the torus. Of course, it's a free boundary problem. My domain is unknown. Yes. Okay, so it's a free boundary problem. So the first thing you do when you want to analyze this problem, or at least that's the only way I know to take the first step, is to rewrite the equations in a reference coordinate system, in a known reference coordinate system. So I constructed a mapping I call phi of u, which maps my current configuration, the unknown deformed configuration of the container, into the canonical reference configuration, which is in fact the domain you see here. So it's the torus times 0,1, something so 0,1 torus squared in the two x1 and x2 direction times the interval 0,1, so you get a cell, right? So bounded, or a cuboid with this torus setting here. Okay, so that's the canonical reference configuration, and of course you pay a price when you rewrite your equations in a reference configuration. You get a lot of garbage terms. So for the sake of completeness, I've written here equations of motion after expressing everything in the reference configuration. Of course, all of these additional terms means that you have a lot of work to do when you at the end want to close your fixed point argument. But to begin with, what you do is you linearize the system and end up after linearizing with the system you see here. So we have the Stokes equation, of course, because we are putting a lot of garbage term on the right-hand side. We have non-homogeneous right-hand side. It goes the mass conservation and momentum conservation equation. But yeah, so a non-homogeneous Stokes equation coupled with our plate equation with the damping term at the moment. When you linearize, the only linear term that remains from the force term, term expressing the force exerted by the fluid on the structure, the only term remaining in my damping term from the fluid is just this pressure term you see in yellow here. So in the linearization, that's easy to express. Okay, so one important step is to decompose, towards understanding this system, is to decompose it in the way you see here. What I simply do is I split the solution to the Stokes equation into a solution of the Stokes equation with inhomogeneous right-hand side in the momentum and mass conservation equation, and another Stokes equation which has homogeneous right-hand side but has a non-homogeneous boundary condition. And via this boundary condition, I have, of course, the coupling plate equation. And now we have, since I split my Stokes system into two Stokes systems, two pressures, one pressure pi, and one here in calligraphic P. And the pi pressure, this is in fact a press term that depends linearly on the U, because you see in this Stokes equation for the V and the pi, U appears in a linear way. In the calligraphic P, you see that the U enters the Stokes equation for where this calligraphic V is not known in a nonlinear way. So this calligraphic P is a nonlinear term with respect to U. So when I split my damping in the plate equation, the damping that comes from the fluid, I have identified at this point the linear part. So I split my damping in a linear part and a nonlinear part. I have this pressure term pi as the linear part, and the rest will be the nonlinear stuff. Okay, so the good maximal regularity spaces that we need to identify have to be the regularity for this problem that I call FSI. Okay, so then I moved on to, well, exactly this point, the maximal regularity space for this the linear, the important linear part of my coupled system. And to begin with, I want to show here maximal regularity in a half space case. So now I move on from the periodic bounded cell to a, well, let's call it a periodic half space. So the first topos T is the time, so the periodic half space is T naught squared times R plus. So in this half space like setting, I analyze the linear part of my fluid structure problem that you see here, and I show to begin with an LQ maximal regularity result. I show that for every H, LQ in time, B1 minus 1 over Q in space. There is a unique solution in, and the solution here is a velocity field W, pressure pi, and a displacement U in the space that I denote here by X of Q, which is, well, in fact, the canonical parabolic maximal regularity space for velocity and pressure of the Stokes equation, and for the solution U to the damped wave equation, I obtain as maximal regularity space here. This space here B2, so B2Q in time, B1 minus 1 over Q in space, intersected with LQ in time, B5 minus 1 over Q in space. So I gain for the velocity field, so that I prescribe the right-hand side here in the plate equation H. I prescribe in this space here, and you see that we gain 4 derivatives in time and 2 derivatives in space. So that's a huge regularization effect that I have in this, at the outset, hyperbolic equation, but of course I have also introduced this heavy damping term. So this is important to keep in mind. Of course, the goal is to remove this damping term, and the price I will pay when I remove this heavy damping is that my regularity XQ space will be much weaker. I will discuss this a bit later. Okay, but let's start with this, with the easy case where I have the heavy damping and
excuse me.
Yeah, sure.
There is a question from Professor Terasawa. So please.
Yes.
So I have a question. So in treating your problem, in the fluid equation, zero right-hand side, and so non-zero right-hand side is not necessary for treating your nonlinear problem.
Yes, I I have, if you go back here, I have split my fluid equation into two. So I have one part here where I have
okay. Stokes pattern. Okay. This I understand.
So you absolutely. So of course this is important there, but so for the moment I focus just on the other.
This I understand.
Of course, I have to take into account also the first one.
Okay, thank you.
Very good. So one thing I should note is that the maximum regularity result here you see here is not optimal, because I have the same LQ in time as I have in space, right? So I have here Q in time and Q in space, and we just saw in Professor Shibada's talk that in fact with an approach using R-boundedness, time periodic R solvers, we can in fact get better maximal regularity results where we have LQ in time and LP in space. I will also address this issue later. For now, I want to focus on however, on this this type of maximal regularity. Okay, so how do we show it? It's quite easy because I have now reduced everything here to a half space case. I have 0 right-hand sides. I can in fact compute the solution explicitly for this system. This is in fact well known. I see this. Go back to Solonikov's paper. He does this all the time, and so probably if you're familiar with this Stokes in the half space, you know how to do this. But for the sake of completeness, let me just quickly do it. So if you take a divergence, if you apply divergence to this first equation here, since divergence of B is 0, you reduce the equation to Laplacian of pi equal to 0. Then you apply the partial Fourier transform in, I do it both in the time and in the two spatial directions where I have periodic boundary conditions. So I obtain an ODE. In fact, this what I do here is in fact also what Robert Dink did in a much more abstract setting in his talk. So it's quite standard. You get now an ODE in the in the x3 parameter, and it's x3 variable, and you can solve this ODE very easily. So you get an expression for the partial Fourier transform of the pi. This you insert into the equations you get by partially Fourier transforming the Stokes system. Then you end up with a system of ODEs again in the x3 variables, which you can solve. Just a standard ODE approach here to get a representation formula for your Fourier transformed velocity field. Finally, you apply or you utilize that the divergence of the velocity field is 0, which gives you from this formula an explicit expression for this Q naught function, which you see here. The Q naught function, this is the constant. So we fix the two Fourier parameters L and Xi and solve, of course, our ODEs with respect to x3. So we get so the constant that appears in the solution is I call the Q naught, and for this Q naught we get a formula by finally noting that the divergence of U is 0, and this you see here. So this formula you see here. But the Q naught, if we just go back here, the Q naught, this was the constant that appeared already here in the equation for the pi. And if we set the x3 variable to 0 on the surface, then we have the pressure on the trace of the pressure on the elastic structure. And this is this pressure we now have expressed by simply solving the ODEs in an explicit manner in terms of the partial Fourier transform of U, in fact, and here a symbol. So we insert now in our plate equation, where we have this pressure pi here, we insert the explicit formula that we have computed, and we get a very beautiful equation here for the U. So our displacement field U of the elastic plate in this Fourier space corresponding to the partial Fourier transform satisfies this equation. And now, of course, we can divide by the symbol here. It's in fact not zero, except in the origin, because we have here, of course, a hyperbolic part. But when the hyperbolic part disappears, we have here imaginary terms that are non-zero. So it's only zero in the origin. Now I made one assumption in the theorem, namely that the data in the this H is the data in the plate equation has a zero time average. Having zero time average means that in the Fourier space corresponding to the partial Fourier transform, I have this equation. So this time average equal to zero means that the Fourier coefficient with respect to the time Fourier transform at zero. So the Fourier coefficient at zero of H is zero. So this means that I can write H, the Fourier transform of H here. I can multiply this 1 minus the Chirac delta measure, which is a function for this simple set group here. I can multiply it to H, and it doesn't change my H hat, because H hat is zero when L is zero. So I have this identity, and this I utilize in my representation formula for the displacement U, because now I have here due to the formula up here, I have in my numerator a term which disappears when L is zero, and L is zero. This means that it vanishes as it's exactly the zero of the denominator. So I have in fact here a well-defined expression for U. Of course, in order to analyze what type of regularity I have for U, or more precisely, how much regularity gain I have with respect to the data H, I have to analyze the symbol. And the symbol has, of course, a hyperbolic part, which here is due to the dt squared minus or dt squared plus Laplacian, the plate equation, the hyperbolic part, and then I have some terms here, imaginary terms here due to my damping terms. So I have one damping term, the first damping term here, which is the Kelvin-Vogt internal damping that I introduced, and then I have another damping term here, which is from the fluid. So I have two damping terms. But now I can see how much does the two damping contribute to the regularity of U. So I can quantify the two damping effects. To be even more precise, when the hyperbolic symbol here vanishes in this region here, I see that the strong damping term, psi squared, has the order L squared, and this in this region is equivalent to psi to the power 4. So this means, in fact, that I gain. So from this observation, we see that we gain 4 derivatives in time. 4 derivatives in space and 2 derivatives in time for U with respect to the data H, due to this damping term. And if we analyze the other damping term in the region where the hyperbolic symbol vanishes, we get here the other damping term in this region, in the critical region, grows to the power 3/2 with respect to the L, so that's the Fourier variable for the time, and to the power 3 for the spatial Fourier variable psi. So the other term, if we did not have the good damping term, I would gain only 3/2 derivatives in time and 3 derivatives in space. So what we see here is that the internal damping mechanism that I introduced, Kelvin-Vogt damping here, dominates, in fact, the damping that comes from the fluid. I need, to begin with, in order to get this maximal LQ regularity, I need this additional damping. And the interesting question is, of course, how much lower can I go when in order to or how much lower can I go before I lose maximal LQ regularity? Okay, let me try to explain a little bit more what I mean by this. So here again, the representation formula, we denote the multiplier by capital N. And as I just explained, we have we see that due to the damping term, we gain 4 derivatives in time and 2 in 4 derivatives in space and 2 in time. So just if we just look at the boundedness of these symbols, then by Parseval's theorem, if we are in an L2 setting, well, then we get the 4 additional derivatives in time and 2 additional derivatives in space directly from Parseval's theorem in an L2 setting. But if we go to an LP setting, we need more sophisticated analysis of the multiplier in order to get the same result in an LQ setting. And this additional, so the interesting thing is that if you remove this, if I do it in red here, if I were to remove this heavy damping term, then I would still get some result by Parseval. I would get 3 in space, then I will get 3/2 in time. Parseval gives me this, but the sophisticated analysis gives me absolutely nothing if I remove the heavy damping term. So that's why I need to get maximal LQ regularity. I need more damping than the fluid gives me. So that's why I put it in there to begin with. When I take it out in my next talk, you will see I cannot get LQ theory anymore. This is not surprising, in fact, because we are dealing here at the outset with a hyperbolic equation. And I read some years ago the books of Hermander and his papers, and he has some rigorous proof that you cannot get LP theory for when you are in a framework of hyperbolic symbols. That I would be even, well, I'm not totally sure, but certainly I cannot prove LP maximal regularity if I only have the damping coming from the fluid. Okay, so that's a lot of discussion about this symbol here. Let me move on. Well, okay, so so how do you prove this maximal regularity theory? Okay, you could use, that would be the sensible thing to do, to use this approach of Shibata that he explained in his talk. Then you get, in fact, better maximal regularity via the R solvers and the R boundedness. We get maximal regularity with different exponents Q and P in time and space. But just to explain to you why do I not get the LP regular or the LQ maximal regularity when I have only damping from the fluid? Let's look at a simple proof of this LQ estimates. So one thing you can do is you can take your symbol, which was originally, of course, our symbol was defined on the torus. You can extend your symbol into the Euclidean setting. I do this by using a cutoff function for the delta function in the numerator, and the denominator. Well, I had here a algebraic expression, so I just extend that canonically Euclidean setting. Then I have a function here, calligraphic M in Euclidean, defined in Euclidean space, which with the property when I restrict it to the dual group of my torus, namely z times z squared. I have the one time torus for the time and torus squared for the space. So so this is my dual group in my original torus setting. I have scaled here so that I don't get too many nuisance factors in my formula. But when I restrict my calligraphic M to this torus dual group, I go back to my capital N. I go back to my original multiplier. Okay, so now you can verify that basically now you can verify that the conditions in the Marcinkiewicz multiplier theorem are satisfied for this calligraphic M in Euclidean setting. Of course, I need Euclidean setting to employ Marcinkiewicz multiplier theorem, and you can check in this case here that this Marcinkiewicz condition is satisfied. So Marcinkiewicz theorem gives me for the calligraphic M that is an LP multiplier. This argument, this is precisely the argument here where I need the heavy damping. If I remove the heavy damping, I can no longer show the Marcinkiewicz condition. So if this heavy damping goes away, this is no longer true. Or that these boundedness of these derivatives, weighted derivatives of my multiplier, and I don't get LQ maximum regularity. So there's this is an interesting question here. So this is a heavy damping, and but at what point? That's the question. At what point, if I lower the order of the damping, at what point does this argument? At what point can I show validity of the Marcinkiewicz condition here? I don't know. Maybe also this approach of that Waseda talked about could give shed some more light on this issue, the dominance, or how much additional damping do I need in order to get maximum LQ. Okay, so as I said, the Marcinkiewicz multiplier theorem gives you that's the calligraphic M is an I call it the LQ multiplier in the Euclidean setting. And then there is this Deleuze's principle that also Professor Batter mentioned in his first talk, which you can use to deduce that in the original torus setting, your original multiplier, the one you extended in order to get calligraphic, is an LQ multiplier. So that's how we get the theorem that we have. Well, we can show this boundedness of calligraphic M, and we can also show it if we repeat the argument with two derivatives in time and fourth order derivatives in space. Using this argument, we get the LQ. We get in fact LQ a priori estimates, of course, which we wanted to prove. Okay, okay. So here you see the influence that the additional damping has on the maximal regularity. This I needed really only to employ Marcinkiewicz multiplier theory. I'm very curious at what point, what type of damping lower order than the heavy damping I have here still allows me to utilize Marcinkiewicz multiplier theory, and that will shed some more light on on the limits of these LQ estimates. Okay, so this was the LQ estimate for the displacement field U. Similar estimates can be obtained for the velocity field W and the pi. Okay, so another remark, of course, I'm using very heavily here that I can analyze my my solution U in terms of the symbol on my spectral calculus. And my spectral calculus is just the Fourier transform, this torus half space setting and the torus in time and space with the periodic boundary condition. Of course, if I choose more complex geometries, I can no longer, I have more complex spectral calculus, and I can no longer, I guess, I'm not sure, but I probably do no longer have nice pseudo differential operator, or my damping, linear part of the damping, I can no longer express probably as a pseudo differential operator as I can here. So that's challenging. So if you change to more complex geometries, this argument also becomes more complex. Okay, let me move on to finalize now the argument. So I have talked now a lot about the half space because that's the core. When you want to understand really and quantify the damping effect from the fluid, you see it in the half space, the case that I just treated. But of course, I want to prove my main theorem in my original domain, this periodic bounded cell. So now we go through the somewhat standard steps. So weak solution. We have to start somewhere, so we start by establishing a weak solution. Here is our, I'm still in the linearized setting, by the way. Okay, weak solution, I do by, I mean, you can do it in various ways, but I did it by first Fourier transforming a linear equation with respect to the time torus. Then I get this resolvent type problem with resolvent parameters L in Z, or if you like IL everywhere on the imaginary axis. So this resolvent type problem I solve with respect to weak solution. So I find a weak solution with energy methods, define an appropriate space. In the space I define a space where certain properties, where the functions have certain properties, the boundary coupling condition on the boundary, and the average, the mean property that we use is this mean over the disk is 0. Okay, so that's the natural space, and then you find an energy or this linear form, which here I call B, with the standard method testing with a function from my space calligraphic V, integrating by parts, you end up with this linear form here, and then you can analyze this this form and show that it's coercive, and by Lax-Milgram you get a weak solution. Okay, so that's pretty standard. I'll move on to next issue. Once you have a weak solution, we need a pressure term. The pressure term we construct in the same way that you construct pressure as for Stokes problem. I have here Stokes problem. I simply look at my Stokes problem, construct the pressure for the Stokes problem, and then I have to normalize this pressure appropriately, and then I get a pressure for the full problem. That's not a big issue. Also the regularity, once you have a pressure, you can get higher order regularity in an L2 setting, by standard methods. In fact, for the U, I have a direct representation formula, which gives me immediately a bootstrapping, a method to bootstrap my way into higher order regularity. And for Stokes, we know regularity theory for the resolvent type problem. So that's not an issue. Showing first existence of a weak solution, let's assume here that we have data that are super smooth. Then we can show existence of a weak solution with standard Lax-Milgram. We can bootstrap our way into any regularity we want when we start with the smooth data. So we find, in fact, a solution with energy methods in the maximal regularity space. But so what is the challenge? The challenge is now to get the a priori estimate. That's the challenge. So we know that there exists a solution. Now we need to get the a priori estimate. And for this a priori estimate, there is one big challenge, and this is the pressure term. Now, remember, I have the Q estimates, maximum regularity estimates I have in the half space. But I want to show existence of and a priori estimate in my bounded container cell. So I need to localize. A very simple localization in this case, but nonetheless, I need to localize. And what happens when you localize Navier-Stokes equation? You get a pressure of lower order on the right-hand side after localizing and utilizing your half space, whole space a priori estimates. You end up with a pressure term of lower order on the right-hand side. Estimating this pressure term is not easy. There is a trick I learned from Paolo Galli some years ago, and I like this trick a lot because it gives me a way to estimate this pressure. And here you see, but the result of applying this, let me call it Galli trick. I think it's from him. Whenever you have a solution to our linearized fluid structure system, VPU, you can estimate the lower order, so just the LQ will in fact L3 half time Q norm of the pressure in terms of the velocity field, the displacement U, the data, and also here some velocity stuff. So I can get rid of this pressure term. Okay, so how does this pressure argument work? Well, here we have our coupled fluid, linearized fluid structure system. I put divergence equal to 0, so I'm cheating a little bit here. So later, when I do the full fixed point argument, I have to lift some inhomogeneous right-hand side divergence equation. But for the moment, I treat the inhomogeneous right-hand side. But I have the homogeneous divergence right-hand side, but I have inhomogeneous in the momentum equation, and here, of course, also inhomogeneous right-hand side in the plate equation. Okay, so this is my linear system. Now, I take some test function phi, which is smooth and smooth up to the boundary. I should have put here overline over the omega. Okay, so it's smooth up to the boundary. Now I test my equation. I'll simply multiply the Stokes equation here with the gradient of this the phi test function, and then I integrate by parts, as you do, and then you see I test the gradient p here with the gradient of phi. This gives me this integral here. Then of course I have the Laplacian of b times the gradient of phi, and then I do integration by parts. And so I didn't do the integration by parts. I just have the Laplacian term here. dt of v times gradient of phi. Here I do an integration by parts. Since divergence of v is 0, I end up with a boundary term. In the boundary term, I can replace dt of u with dt squared, sorry, dt of v with dt squared of u. So I get a dt squared of u times gradient phi, but this dt of u I express in terms of the Laplacian u and this damping here. And finally, also with a pressure term here times phi. So this is the term you see here. And this is important. In fact, I have to admit, when I first wrote my first paper on this fluid plate equation, I made a mistake in my estimate of this pressure term here, and so I gave this problem to my PhD student and asked him fix the mistake. And I said, you can just use the Galilei trick. This will work. And he tried and he tried and he tried and he didn't get it to work. And because in the Galilei trick, this term here does not appear in Galilei's papers. But here it appears because we have a coupled system, so we have an additional pressure term here. Now, why is this important? Because the next step is to solve the dual equation. So here basically we have a weak form of a Laplace equation, namely this Laplace equation you see here, but it's not the usual Laplace equation with Neumann boundary condition. It's a Laplace equation with a Robin type boundary condition. And this was the reason. If you apply the Galilei trick, normally you use here just a dual equation. You use Laplacian with Neumann boundary condition. But here we have to, in fact, introduce Robin boundary condition. So that took a while to figure out that this was how to do it in the right way. Anyway, so now you look at this dual equation and find a capital phi, and then via Sobolev embedding, you estimate importantly the first order, the gradient of the phi. You use a Sobolev embedding, and then you use a standard elliptic a priori estimate, and you get this type of estimate here, gradient of phi. And then you look at pi dot eta. Eta is the right hand side of the dual equation. Well, the eta is equal to Laplacian of phi, so you get here pi times Laplacian of phi. And when you now integrate by parts, you get the same left-hand side that I had after testing my original system with a test function. But now, so I go back to the first equation I had. This is the dot, 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 and express everything in terms of a u and a v and the data times gradient of phi. And then I only need to do a Hölder estimate, and using a duality argument, I get this LQ norm of P under control in terms of the gradient of phi times the norm of the velocity field and the data and the displacement field. And of course, in my duality argument, I then I replace the norm of the phi with the norm of the eta, and then do a duality argument, and I end up with the estimate of the pressure that you see down here. Okay, so that's an important step. It's very difficult to get rid of this pressure term, and here in this fluid structure system, it took me a long time to figure out that I had to use the Galilei trick with a different type of boundary condition. Okay. Well, once you can estimate the pressure, you can do the localization argument. We have the LQ estimates from the half space case, and well, after localizing, because we can estimate the pressure in the right way, we get the maximal regularity here with the a priori estimate. So that's just the linear theory for this problem here. Okay, and well, the proof, I'll just go through it very quickly because I already told you what the proof is. We use a localization argument, so I use a cutoff function here, eta, to decompose my original solution in the container to a solution to a whole space solution of the fluid equation, and sorry, half space. H is for the half space, of course. So half space solution here and a whole space solution. And for the half space solution, we have the estimate, and for whole space is even easier. We have also maximum regularity space in the whole space, but due to the cutoff, you have here a pressure term of lower order on the right hand side. You cannot get rid of this pressure term by say the classical contradiction argument. Why, by the way? Because I don't. there's a way to get rid of lower order terms on the right hand side in such an a priori estimate. I have lower order v and lower order u and lower order in p. The classical argument is a contradiction argument where you use a compactness, compact embedding. So you can get rid of these lower order term if the space, subular space corresponding to lower order term on the right hand side. No, I have to express it differently. If the subular space corresponding to the higher order term on the left hand side is compactly embedded into the subular space corresponding to the lower order term on the right hand side, then you can get rid of these terms with a classical uniqueness argument. But for the pressure, we don't have this compactness because I only have the gradient of the pressure under control on the right hand side. I don't have any time derivatives of the pressure under control, so I don't have any compact embeddings. So that's why this pressure is always a challenging term to get rid of. But so this Kyed trick, which provided me with an estimate of the lower order pressure term, is very crucial. Okay, the rest of the lower order term you can get rid of with the standard contradiction argument based on compact embeddings. Okay, now I have not said anything about, well, actually one thing that I needed to assume to utilize my half space estimate was that the time average of the age was 0. This was important for the half space estimate. So for general data, where the age and the f for that matter too do not have 0 time average, I need to decompose these two data into what I call a steady state part and a periodic part. And we still need to solve or to establish estimates with respect to the steady state part. But this is, I pressed something I should not press. This is a question of solving the corresponding steady state system. And this is in a bounded domain here. This is no problem. I have steady state Stokes and I have the Euler Plastic for the plate equation steady state part. One argument before I finish my talk is one comment here before I finish my talk. I cannot get this type of maximal regularity estimate in the half space for the time periodic problem. This is due to this steady state part here. The steady state part, I cannot get any. If I were to work here in the half space instead of in this total here, then I could not get good a priori estimates of this Euler-Plastic problem. So the steady state part means that I cannot go into the half space for my full result. So this is different. The difference to the corresponding initial value problem. The corresponding initial value problem you can work very nicely in the half space. I cannot do this here because I also have a steady state part, which do not like half spaces. Okay, or unbounded domains in general. Okay, so that's it for the linear part. And then in the main theorem, we can now use the maximal regularity for the linearized system to show existence for the fully nonlinear problem of a solution when the data is sufficiently small. We show existence in this total setting, so we get a time periodic solution for the nonlinear problem based on a fixed point argument and the linearized maximum regularity estimates. Okay, so these techniques were I developed with my PhD student, and you can read this paper here if you are interested. Okay, so in my next talk, I will show that we can in fact apply the better approach that Professor Shibata introduced to get even better maximal regularity results also for this problem. So this is another application of this result that Shibata introduced. And then, of course, finally, I also want to look at the undamped elastic plate. So that's my final goal, in fact, the undamped elastic plate. But as you will see in my next talk, I cannot get so nice results in the undamped case. So let me stop here. Thank you for your attention.
Thank you so much for your very interesting talk. Are there any questions or comments? Professor Terasawa, please.
So for treating the undamped case, you use basically L2 theory?
Yes, I can only do L2 theory.
Okay, but that it's not so satisfactory.
Absolutely. Also, because yes, it's a very good point. Because remember, at the very beginning, I talked a little bit about the plate model. It's not to me, it's not really the physically correct model. To me, it's what I think should be the final goal would be 3D elasticity, coupling with 3D elasticity, or membrane models where you only have a second lower second order derivatives in the elasticity equation. But then the L2 theory completely fails. So you're absolutely right. The L2 theory is not as satisfactory as the maximal L2 regularity. And in the on-damped case, it's to me, I know only of L2 theory. I will talk about this.
Okay, thank you.
Are there any comments or questions?
Excuse me, may I don't know how to push the hand. Okay, may I ask you? So you start L2 theory, I mean, in something in order to get maximal regulated. Yeah, because it's a little bit faster for me. So you start, in order to get maximal regulated, you start L2.
Yes, just to get existence of the solution and
the L2 case is maybe I always think about the R boundedness, but L2 case is maybe the R bounded is rather trivial. Therefore, you can get a maximal regulated. But then going to the LQ is the local regulated or something. Wow.
So you are suggesting to first obtain L2 maximal regularity and then
L2 and then going to then you get to the LQ estimate for the pressure, and then maybe you go to the regulator for the LQ regulator. No, I'm maybe wrong. I don't know. My question is also that can you treat maximal regulator directly for the LQ R boundedness or not?
So you for the half space problem.
Corner is a very singular, at least lambda equals 0 or something.
Are you talking about the on-damped case?
Yes, sorry. So the last part was.
Yeah. So the on-damped case,
no. Just your talk today.
My talk today. Well,
today,
my talk today, I can. In fact, you have with your student. You showed some years ago the R boundedness of the corresponding resolvent
I'm
solution
thinking
operator.
You consider the half space. No, I mean the periodic. So it is a two-point ordinary differential equations, I guess. Then,
okay. So it's a little bit different than yours.
And then can you show that the R solution operated in LQ sense of your solution? Because you start L2, and then as far as I understood, you start L2 theory.
Yeah.
And then.
But I do not have maximal L2 regularity, by the way.
Only just the existence of solution.
I just have existence of the solution. Yes.
So. No, I'm sorry. Maybe I want to see some of the, because for me it is fast.
Yeah, sorry.
Yes.
I had one.
Please repeat a little bit. Okay,
so this was probably the slide that you were thinking about. Here, to get this existence of a solution in the maximal regularity space, I used only L2 theory and. But here, of course, I exploit that the data is super smooth. So I just find a weak solution, and then a corresponding pressure, and then I exploit that my data is so smooth that I can get into any type of L2 space of this type here.
So you get
and then from this type of space, I use a Sobolev embedding to get into my LQ space. But of course, I lose my a priori estimate in this way. So I don't have any maximum regularity.
In the L2 sense, yes. This I can catch. Then you go to the LQ. First, you estimate pressure P in by using some of
This is the pressure.
Now you go to the yes, this one. You show this kind of LQ regularity. No.
Yes. So this is LQ for the pressure.
Yeah.
And this pressure, I need this estimate because my localization argument produces a pressure term of lower order on my right-hand side.
Okay.
So
you raise up the LQ is in. So your solution first you start L2 and then you go to the LQ. Can I?
But yeah. So I start with an L2 solution, yes. So I have a good L2 solution, and it is as regular as you want, because I start with smooth data. And then I want to show the estimate, the LQ estimate for this L2 solution.
Yeah.
So I decompose it into a... So
okay, yes, this I catch. Yeah, okay. This you get the LQ, yeah, in the pressure. Yeah. And then finally, and then after that, you use some kind of regularization for some Laplace operator or something like that.
Well, no, because I already have my solution already. So this is the solution I get the L2 theory. And if I assume that my data is smooth, then the solution is also smooth. And then, but I need for this estimate here, the actual LQ.
Okay.
I need the half space and also whole space. I did not mention whole space estimate because they are easy. The half space estimate.
I see.
So the difficult thing is to get the a priori estimate for the half space. And so I use this a priori estimate for the half space. This I use for my function that lives in the half space that I produce with the cutoff. But of course, the cutoff of the function gives me
This I understood. Okay,
I have a low order pressure term.
Yeah, and then, but okay. I see.
So excuse me. So the time is approaching.
Sorry.
I would like to stop here. So let's thank speaker again.